calculations. So what we will do is our goal is to calculate density of state. I gave you last time one definition, formal definition, in terms of how to calculate it, but let me give you another definition of the density of state. Density of state, verbally, means the number of state per unit of energy. So this is dN over d energy. So this is how many states are placed in the interval between energy and energy plus d energy. So I fix some value of energy, and I take a little deviation, and I'm interested in knowing how many energy levels are sitting between this and this energies. And this is what density of state tells me. Okay, I choose a box, and you remember that the X node, so I made a shift of the orbit in the direction of X node, which is E Py over H C. Sorry, it's a C Py over EH. So I would like to be sure that this centrum of orbit is within the box. So I'm saying that C Py over EH is smaller than that. So therefore, for my Py is EH over C L1. So L1 is the size of my box in X direction. At this very moment, it is very instructive to define something which is called magnetic length. So you see that the dimension of Py is, if I put h bar equal to 1, is inverse dimension of the space. Therefore, I would like to write it as L1 divided by AH squared, where magnetic length AH is inversely proportional to magnetic field EH over C. So it's a C over EH to the power 1/2. So this is magnetic length. Okay, and then I may say that d and z is actually d p z L3 over 2 pi h, and d and y is equal to dpy L2 over 2 pi h. You remember these two variables led to exponents, and the quantization occurred in the next direction when I derived the Schrödinger equation. So if I integrate it from 0 to maximum value of Py, I will get that Ny is equal to L1 L2 over 2 pi h a h squared right? And total number of states in the interval of energy and epsilon over the energy is equal to ny times d and z. So I integrated out all states in xy plane. So this is why only nz remains. I'm plugging in that. So this is L1, L2, L3 divided by 2 pi h bar square ah square and dpz. Therefore, the density of states, you see that this is volume. So this is dn per projection per spin, and total dn is equal twice as large. So now I recall that I have a spin. This is a volume over 2 pi h square ah square times dpz. So you see that the degeneracy occurring in the system is in fact proportional to magnetic field. So the larger magnetic field is, the more levels are accumulated into Landau levels. So these are Landau levels. Okay? So then what I need to do is to express my Pz in terms of energy. So Pz from this formula is a plus or minus square root over 2m, energy minus h omega c n plus 1/2. And if I would like to define the density of states now, and I incorporate plus and minus for Pz in terms of modules, so what I need to do is divide by d energy. It's 4 times. 4 comes because 2 is here, and 2 comes from summation of plus and minus. Volume 2 pi h square ah square d modulus Pz over d energy, where Pz is given by this formula, so this derivative will give us inverse square root. So what I need to do in remaining 20 minutes, and what be unfortunately kind of involved integral calculation, is to use this density of states in order to calculate the thermodynamic potential omega. And what I suggest that you repeat this calculation yourself, because I'm pretty sure you will not be satisfied at the first glance, and you will not catch everything, and in the way of repeating you will have questions, and then you will ask. So at this very moment, if it is clear logically and mathematically what is done up to that point, I will erase everything and start to calculate omega. So you know, theoretical physics, and maybe most part of theoretical physics, is calculations. So, of course, we should always understand the route and where we are going, and whenever it's possible to anticipate the results, but we are about to calculate the number now. Okay, I will need probably whole blackboard in order to do this. thermodynamic potential omega is equal to minus 4dt over 2 pi square ah square. So we call the omega is minus t sum over I log 1 plus e to the power mu minus epsilon I over temperature. So I'm writing this formula now, and here it's integral from 0 to infinity d energy summation over all levels, discrete levels, d modulus pz over d epsilon. So this is what density of state was, and here is logarithm 1 plus e to the power mu minus epsilon over temperature. So this is a monster I'm going to calculate, where pz, modulus pz, equal to square root over 2m epsilon minus h omega c n plus 1/2. It's very inconvenient to have a logarithm in the formula. So therefore, the first thing, I would like to get rid of the logarithm. In order to do it, I will integrate by parts, and then instead of logarithm, I will have Fermi distribution function. Okay, so this is then u, and this is dv. This is dv. So I will keep all coefficients because I'm fighting for the coefficient in front of expression as long as I'm correct in anticipating what's going to be obtained. So this is minus 4dt over 2 pi square ah square, and here I have to put a bracket. So now pz gives me the square root 2n epsilon minus h omega c n plus 1/2 times derivative of the logarithm, which is 1 plus e to the power minus mu minus epsilon over t minus e to the power mu minus epsilon over t 1 over t. Yeah? In the limit 0 infinity minus remaining part. Minus, and I will put plus. Here you recognize a Fermi distribution function, 1 over t, integral from 0 to infinity. Now I have to put dE sum over n. Here it's 2m epsilon minus h omega c n plus 1/2 to the power 1/2 divided by e to the power epsilon minus mu t plus 1. So let's look at this expression and first conclude about the term, first term in the bracket. You see that in principle, No. Sorry. I'm too fast. So this one is correct, of course. I already plugged in, but here it should be log 1 plus e to the power mu minus epsilon over temperature in the limits 0 and infinity. Sorry. Of course, here it's not 0 because the summation is defined where the argument of square root is positively defined. Actually, I should say that n from this formula, the argument should be positively defined, changes from 0 to maximum value. So n is smaller than epsilon minus h omega half divided by h omega c, right? So what I'm saying, that minimal energy is then h omega half, which I ignored in this rigorous expression, but now I have to recall it, and I'm saying that this expression is 0 both on the lower limit of integration, because then the square root meets the requirement of minimal energy, and it's also 0 at upper limit, because if energy is infinite, then the exponent is 0, the log of 1 is 0, and therefore I have 0 everywhere. So what I do, I drop this term. Okay? And we write expression. Now I may cancel the temperature, which stands here and there. And this appears due to derivation of this logarithm. So I integrate it by part. Minus is replaced by plus just because the derivative of this is minus Fermi distribution function times 1 over temperature. So in total I have again minus, the temperature is dropped, 2 pi squared 1 over h squared, and the remaining integral is from 0 to infinity d epsilon. Summation over n is taken from epsilon minus. You remember that h omega c half is mu Bohr times magnetic field. So this is epsilon minus mu Bohr h over 2 times mu Bohr h. And the expression, I repeat it, 2m epsilon minus mu Bohr h to n plus 1 to the power 1/2 divided by e to the power epsilon minus mu over temperature plus 1. Here, mu is chemical potential, which I will replace by Fermi energy soon, but at this moment, please don't confuse it with the magnetic moment. I put always index B for Bohr magneton. Okay, now I'm saying let me confine myself by temperature equal to 0, and then I replace the Fermi distribution function by step function, and therefore I replace energy by maximal energy as a Fermi energy. This will give you big simplification, but this simplification is justified because in reality temperatures are much smaller compared to Fermi energy. So what I need to say that I'm in this limit, and this is always like that. This is 4v over 2 pi squared 1 over eh squared, and here I have integral from 0. Let me replace summation over integration. 0 to minimal energy to mu bar h to n plus 1. This is this minimal energy to chemical potential, to Fermi energy. And here I have 2m epsilon minus mu bar h to n plus 1 to the power 1/2. So this limit comes from minimal energy. So epsilon should be bigger than something depending on n, and this is maximum energy. And I replaced integration over summation and summation, d energy. So still no approximations apart replacement of the Fermi distribution function by step function is done. But now I can take this integral. It's not a big deal. I can proceed with integration over energy and then proceed with summation in approximate way. So what I have now is the integral over x to the power 1/2 dx is 2/3 x to the power 3/2. So I'm writing 8v over 3. It comes from 2/3. 2 pi square 1 over eh square. The coefficient remains, and what is remaining here, it's sum over n. Fermi energy minus mu bar h to n plus 1 to the power 3/2, and n changes to Fermi energy over 2 mu bar h minus 1/2. So as I said, the magnetic field is so small compared to Fermi energy that I can replace upper limit by infinity, and also discretization of level associated with magnetic field is so small compared to Fermi energy. So I can replace summation by integration. And in order to do it, I would like to use the Poisson formula, which I will give you without proof. It tells me how discrete sum can be replaced by integration if I have some function which depends n of 1/2. Then the approximate formula is integral from 0 to infinity dx fx plus 1 over 24 f prime at 0. So this is Poisson summation, which you should actually have heard about from mathematics and advanced statistical physics. I will use this formula where function f is clearly given by this one. So f in my case is equal to Fermi energy minus h omega c n plus 1/2 to the power 3/2, and f prime is equal to 3/2 with respect to x. Fermi energy minus h omega c. This is x to the power 1/2 times minus h omega c. Right? I will even remove n and write x here. Oops. X. And clearly, at x equal to 0, this is the Fermi energy to the power 1/2. So, look, when I replaced summation by the integration, what I will do? Let's look at this multiplier. It is EH over C. So it's proportional to magnetic field. When I will replace summation by integration, I will introduce a new dimensionless variable y, which is h omega c x. So then I need to multiply by omega c in order to have this variable dimension and divide by omega c. Therefore, the contribution from the first term will not depend on the magnetic field, because I have to divide it by omega c, and omega c is proportional to magnetic field itself. At home, please use this formula and calculate this term. What I will concentrate on is delta omega, which depends on the magnetic field. Because I will differentiate this magnetic field with respect to magnetic field and calculate thus magnetization, and the second derivative will give me susceptibility. So I'm using only this simple form, which will then contain magnetic field. So I'm collecting all coefficients, and you do the same at home. So this is minus 8/3 V over 2 pi square EH over C, 1/24, 3/2, minus mu Bohr, 2 times mu Bohr H times square root over 2m and times Fermi energy to the power 1/2. So first of all, you see that the total sign is plus, because 1 minus comes from here and 1 minus comes from there. If I collect all multipliers, all coefficients, what I get here is 1/3 V over 4 pi square EH square over C, Fermi energy to the power 1/2, square root over 2m, and here is Bohr magneton. You see that here I have almost Bohr magneton times square of magnetic field. So I will multiply and divide by the mass. And also recall that 2 times mass times square root of Fermi energy is the Fermi momentum. So what I have in total, the delta omega, depending on H, is equal to plus V over 6 mu Bohr square H square times density of state at the Fermi energy. Okay, then magnetization per unit volume is minus 1 over volume d omega over dh. So this is equal to minus 1/3 mu Bohr square H density of states at the Fermi energy, and susceptibility finally is equal to minus 1/3 mu Bohr square density of states at the Fermi energy. Good. So the number which I was looking for here is equal to 1/3. You may ask me, how about diamagnetic metals? We have a copper which is diamagnetic. How can it happen that the number which we get here, and which is 1/3, tells us that there is no diamagnetism in the nature whatsoever? In order to answer this question, we need to think which mass is contained in Bohr magneton for paramagnetism and for diamagnetism. So while the mass in the Bohr magneton here for paramagnet is clearly bare electron mass. It doesn't have to do anything with the band structure, and all band structure effects are fitting. Here, the mass associated with the magneton Bohr in this formula knows about effective mass, about orbital motion of the electrons. Therefore, and I would like to write it here, we may say that chi para over chi dia is equal to -1/3, but it's a ratio of a mass to effective mass squared. So now we see that this ratio of it's other way around. It's dia, of a para, since diamagnetic, excuse me. Since now this ratio encodes also the knowledge about masses, and as I tried to convince you during the last lecture, the masses, effective masses, can be as larger as smaller compared to electron mass. This ratio can be either big or small compared to 1, and therefore the diamagnetism is allowed by this theory, and there is no contradiction between what we have derived and what exists in the nature. Okay, that's all. Questions?
Is there any circumstance that we have effective spin of electron in quasi-electron beam?
Effective spin, no. Spin is discrete quantum number. You know, of course, when you talk about materials, then some atoms can form clusters, and in these clusters, spin can be summed to some value. For example, mangan in semiconductors like to form tetrahedra in the structures, and since mangan is characterized by the spin either 3½ or 5½ this is the spin of manganese atoms, then one can have large spin just because these tetrahedra have ferromagnetic orientation of the spin. But it cannot be arbitrary continuously number. It can be either discrete number like 3½ 5½ 7½ or whatever, but 2, 3, 4, unlike mass, which can be continuously renormalized, and this ratio of bare mass of electron and effective mass due to band structure can be arbitrary. Yeah. Any more questions? Look, as I said, today we met with some not really serious but lengthy calculations, which I wanted to show you just in order to tell that we are dealing with many-body physics. Many-body physics is a complicated subject, and we will do calculations. And most of the course will be devoted to doing calculations. But I encourage you to repeat it step by step, to look at Abrikosov's book, to try to reproduce each and every step of this calculation. And if you are unhappy with something, unsatisfied, please write down questions and please come to me and we discuss these questions. So it's both physics, understanding of the physical nature, origin and consequences of effects, but also I will be happy if be able to teach you how to do calculations and how to proceed to some result which can be then interpreted. Okay.
didn't open.
I mean.
You didn't open the message.
No. At that time I didn't receive it.
Ah.
After I ready to. Yes. Oh, I didn't know that. My God.
How was your calculation?
Oh, I think it.
I have factor actually wrong. I don't know what's wrong with me.
Now my problem is to calculate G.
G?
G, yes.
Is it?
I want
changing
to G Fermi.
Fermi,
yes, I want to
but
find
actually,
a relation.
my problem is here. What is the coupling for GZ from the beginning, the matrix element? Here, why we didn't take over 2?
We don't need over 2.
Why?
Because, do you remember I calculated first.
When you calculate, you get 1, 2.
No. Oh!
This one, 2.
No. Let me. I started from here, and when I started from here, I divided in 2 parts, and first one is for electromagnetic, and second one for GM.
Yes.
Okay, and now there is no any factor here.
No, I mean when you introduce gamma 5.
Gamma 5. Oh, you mean we need? Okay, but in this case, we say in general you consider this A and B,
Yes.
not 1/2. 1/2 is inside to the A and B. You know, I found A for the up.
You see, yours because you have 1/4 here.
Yes.
Mine I have 1/2. It means I miss 1, 2 outside. No?
Oh, maybe.
Yes, that's why.
But here you should have a factor of 2.
So because when you take the square of this one, you come 1/16, no?
Yes, exactly.
So me, I miss 1/4 outside. That's why I should put 1/4 here. This is my.
Yes, but I think you made a mistake because
my B
oh,
is
no, you're right. Yes. Because
so
this is square.
Yes, square.
So
yes. When I put it square, it becomes 1/4. If I can absorb it here,
yes.
I can put it here.
Yes.
Yes. Because when the way I calculate it, not like this. I just take this one. I put this one. I started from here. I didn't use the matrix sine, cosine from the beginning. You put it there, and I compare. You compare also, right? You compare.
With what?
With this standard form. Why you call this A and B? You compare, no?
Yes, no. I just, I write it. I separate F and F prime up and down.
Yes, of course.
And after that, each of them has a factor, and so I.
You see,
I
you have half here.
Half.
And half, no?
Yes.
So you can put it outside. Maybe you absorb it inside here, inside. Okay, no problem. It's the same.
No. Yes. I just calculate it from inside.
You absorb it here.
Yes.
Me, I bring it out.
Yes. I get it. Differences.
Yes.
Because I consider this A.
Oh, you call it A, okay.
Yes.
And that one is
this B.
B.
Yes.
Okay, no problem.
With 1/2.
And this is your A and this is your B.
Yes.
And that one here you have half, yes. Oh, good. I got my problem because me, I put 2 outside, and when I calculate the matrix element, I didn't add 2 again. So I should put it there. Okay, because your A is twice my A.
Yes. Twice. You twice.
Me twice yours,
Yeah,
yes. Me twice yours, yes. Because if I multiply 2, I will get my A.
And you have also
yes,
a factor 2.
Yes, I have 2 here.
Yes.
So because when I divided by 4 my result, I got 2.39 this for the total decay.
And the parity is violated for neutrino maximally, but for electron no. Not violate, yes. Violate actually, but not maximally.
Yes, violate but not maximally, yes.
Because there is no any zero. Because d gamma, d omega is not zero either in each.
The omega?
I mean the what was
The gamma.
the I mean this the partial.
Here. This one is
Yeah.
not 0, yes.
Yes.
No 0.
This is for neutrino. For neutrino, this is 0 for theta 0.
For theta equals 0, give you 0 for
Yes,
neutrino.
but for electron now.
It's not 0. That's why it's not maximally broken, yes,
Yes.
of course. You put theta equals 0 here, it's 0. But why you have cosine? Here you don't have cosine, sine. Because for neutrino you don't have cosine, sine. No?
Yes, but in the formula,
In the
we
formula.
don't have class. I mean,
Yes.
yes. Now they send. Yes. Now what?
And GR?
We have here.
GR?
Yes.
Are you sure?
Yes.
Because we don't receive any email.
No, it's written already there.
Oh, that's there?
Yes.
Oh my God.
So something happened, yes?
Maybe. Do you remember Goran say maybe I cannot arrive?
I think that's criminality maybe. But
I don't
about
think so.
next Wednesday.
What?
Tuesday?
Monday?
No, next Wednesday.
For what?
Nelly also said that maybe he will not be able to be on next Wednesday.
GR, yes. GR. Monday is not here, but also maybe on
Wednesday also?
Wednesday.
Okay.
Okay.
Good.
I go to library. I have never been there.
Oh,
it's
library is very good place for study. Very good.
You don't need to go and check each section. You just write in the computer which books you need and it tell you the direction. Okay, if you need these books, you have to go section 3, 4, 5.
But sorry, be careful. Maybe some of the staff say you are you from here?
Okay.
Because I know a person from USA University. They come here to study, but they say you cannot stay here.
No.
They say them that you should go out after 4, but I don't know.
After 4.
Yes, after 4.
Maybe.
But they never, I think they never ask. They think that he came for all job or whatever.
Yes, but they ask from her. He's
Maybe you want to borrow a book or want to do something. That's